Here is Marcus Ullmann, and we'll talk about investigating puffs in square duct flow.
Thanks a lot. So my name is Marcus Ullmann from the University of Karlsruhe in Germany, and this is work that was done together with Alfredo Pinelli from CIEMAT and with Genta Kawahara and Atsushi Sekimoto from Osaka University. So the talk is on turbulent puffs in a square duct flow. Let me just start off with a few basic facts on the duct, although many of these things have already been said by the previous speaker. So the laminar flow in the square duct is linearly stable. So in that respect, the flow is quite similar to pipe flow. However, here, at least at the moment, there's no traveling or no nonlinear equilibrium solutions which are available from the literature. On the other hand, in the turbulent regime, a lot of studies have been carried out experimentally and also numerically. And perhaps the most interesting thing in the turbulent regime is the appearance of a secondary flow, which has the well-known 8-vortex pattern, which is, I don't know, I hope it's visible here. So there's a pair of counter-rotating vortices associated to each corner with the direction of the flow such that it's directed towards the corner here on the diagonal and then flowing out on the bisector. So recently we have shown that there's a clear relation between the appearance of the secondary flow and the coherent structures which have a preferential location, which makes this statistically appear as a in a mean sense. But here we are more interested in lower Reynolds numbers where localized turbulence appears. So since pipe flow is perhaps the most similar to duct flow, that's what we are concentrated to compare our results. And the term of a turbulent path has been, as far as I know, defined by Winansky and co-workers in the 70s. And these studies have been taken up more recently and also numerically by Willis and Kurzweil. I think in this conference there's going to be a number of other talks on localized turbulence, turbulence spots, and also patterns in other flow configurations, such as plane quad, plane channel, etc. So what exactly are these puffs? Well, they are localized turbulent flow regions, which are embedded in essentially laminar flow. And they propagate at approximately the bulk velocity. They are sustained over long times. They evidently appear at low Reynolds number, and I might insist that they are not traveling waves, because even if you're moving at the speed of these puffs, they show internal dynamics. So what we want to do here is first of all establish whether puffs exist in a square duct flow. Define the Reynolds number range where they appear and where they can be sustained, and then go on to characterize the statistics by performing phase averaging and, well, relate them in a way to the known result for fully turbulent flow. So we are considering the flow in a straight square duct with a half width of h. We consider the flow to be periodic over a streamwise length of Lx, and we perform DNS with a standard pseudospectral method using Chebyshev Fourier expansion. We're running at a constant flow rate, and we're considering length of, well, principally 100 half width. We have also gone up to about 130. There's, well, we have tried essentially two alternative methods of setting up puffs. One is starting with developed turbulent flow in a long domain, and then progressively reduce the Reynolds number until puffs appear, or until puffs are the only thing which are left from the turbulence. The other method is to start with laminar flow and then impose a localized forcing over a short interval, and then puffs develop after a certain time. Both methods work and generate puffs here, and in the following I will concentrate on the second method. So we impose forcing on the momentum equation, which is applied over a length of 2 pi h for a short time, 2.5 bark units. We use the particular shape of the forcing as proposed by Willis and Kurzweil in the pipe. However, we just extend it to the square cross-section and for a certain finite amplitude. And this is what the flow field looks at the end of this forcing interval. So this forcing function is essentially a single harmonic over this short interval with respect to this large domain. So the field there at this initial time is not very interesting. After about 25 bulk time units, something which resembles a puff appears. We see the full streamwise velocity and then the fluctuation and the pressure field. This is in the mid-plane cross section through a section through the channel. So this is streamwise and this is a wall normal. If we look at the energy of the fluctuations, initially we input energy into the system by the forcing until this dot here. Then thermokinetic energy keeps on growing for short times, and then it saturates and it fluctuates around this average. So next question is, what is the Reynolds number range for sustaining the puffs? First of all, here I have put up the already known diagram of the friction factor as a function of the Reynolds number for short domains, where we have found a critical Reynolds number for sustaining turbulence of about 1080. So that was found previously. So here are the different puff solutions in blue in much longer domains. There's a whole cloud of points. So actually we have several values for the same bulk Reynolds number, because this friction factor is box average. So if you consider having a same puff in a longer domain, this will lead to a different friction factor. Or if you have certain different number of puffs in the same domain, this will also lead to a different friction factor. So actually, box average of the friction factor is not a good measure to distinguish these runs, but here it serves to distinguish the flow from laminar. So the range for sustaining puffs is between 800 and 1025. Below 800, the puffs will decay to laminar flow. Above 1025, the puffs will still appear and will be sustained, but they will spread. So in our computation, they will end up filling the whole domain. In an experiment, they would just spread while being convected downstream. So to compare with pipe flow, here we compare with pipe where the Reynolds number is then based on the radius instead of the diameter. So we get a comparable regime, although we cannot expect that it would be exactly the same. So here I would like to show a short animation of what the puff looks like. So this is zooming in on the central region of the puff, and we're moving with the advection speed of the puff. We're seeing this gray surface is the streamwise velocity, so it shows this kind of bulging around the region where the gradients get larger on close to the wall. And the blue and the red surface are intense streamwise vortices. So we see that these vortices are generated and destroyed all the time, and they have a complicated interaction, just like in wall turbulence. So next, we want to determine the propagation velocity of puffs. So we compute space-time correlations of the streamwise velocity perturbations. Here we have the streamwise separation and time. So we see that the contour lines of the correlation function are nearly straight lines. So if we fit the maximum for two Reynolds numbers, we get that the propagation velocity is indeed quite close to the bulk velocity. So now, knowing the propagation velocity, we can do phase averaging. So here we see the velocity on the axis of the duct, the streamwise velocity in phase average. We see that there are values close to the laminar value of 2, far from the puff, and then the trailing edge of the puff shows a very steep decline of the velocity, so deceleration, and then it re-accelerates more slowly towards the front. So we need to define some reference position. We take the largest gradient of this velocity on the axis to define some origin of our coordinate system attached to the puff. Other authors have used the trailing edge, which would be somewhere here, but it's perhaps more difficult to define. So that also means that a fluid is constantly moving from the back through the puff, transitioning and then relaminarizing, because it's faster than the motion of the puff itself. So here are some velocity profiles along the axis, comparing with laminar flow. So the puff is in black. Behind the puff, basically, we have essentially laminar flow, and then we see how the black line diverges, gets more flatter, and develops larger gradients, and then it relaxes again towards laminar flow in the front of the puff. Here we see the wall shear or the friction factor in terms of the Reynolds tau value on the axis. Far from the puff, we have something close to laminar value. It's not exactly laminar. And then in what we will call the core of the puff, we get to values which are close to the extrapolation of the turbulent wall shear given by Jones' formula. So we defined a core region of plus minus 5 half-widths around the maximum of this wall shear, which will be used for averaging later. Here we see the variation of the fluctuation energy along our domain. So we have here this plane showing the cross-stream fluctuation energy versus the streamwise fluctuation energy. So this is a loop because we're going around the periodic domain, but actually it collapses to nearly a straight line. So we have attached also the coordinates along the path. And we see that the point 5, about here, is the most energetic point of the path. And from here on, it doesn't matter so much in which direction you walk, you would see more or less the same fluctuation energy. We can also add a data point from turbulent flow at slightly higher Reynolds number, but in short domains, so this is fully turbulent. And we can see that although it doesn't match with the most energetic point, but it's more or less in the same order of magnitude. Here we see the profiles of the intensity of the velocity fluctuations in the core of the path. These are the black lines, and the red lines correspond to marginally turbulent flow. And we see, although the levels do not match, especially here in the cross-stream directions, but we see that the overall shape of the profiles is actually quite similar, and specifically the peak here, which can be attributed to the streaks. This brings us finally to the secondary flow, which is quite interesting. So this is the secondary flow found in the core of the path, this Reynolds number 800, which actually exhibits a very nice and very nicely symmetric 8-vortex state. So it resembles very much what is found in fully turbulent flow at slightly higher Reynolds number, but even at much higher Reynolds number.
Sorry, but this is averaged on the left-hand side for the paths?
Yes.
How many paths?
Now this is a single path averaged over 1,000 bulk time units.
All right.
Okay, and then again averaged over this core region of 10 half-widths. Okay, so it corresponds quite well. I mean, if you look closely, there's differences, but not very much. So now, as was already mentioned by the previous speaker, what we have found in marginal turbulence at this Reynolds number is that although the signature is 8 vortices, instantaneously we quite often found only 4 vortices being present, meaning that only 2 walls were actively turbulent, and this would switch in time, and then statistically we get 8 vortices. So now the question was, is the same true for the path, which appears at even lower Reynolds numbers? So for that purpose, we had previously defined what we called an indicator function, which actually shows us how the vorticity is partitioned in the cross-section. So this is a function which takes values between -1 and 1 and measures actually the integral of the vorticity squared over these small triangular cross segments which are delimited by the diagonals. This function would take values close to 0 if the vorticity, the secondary vorticity, is nicely distributed over the 4 sectors, and values close to 1 or -1 if we have these 4 vortex states. So it lets us distinguish between the two patterns. So indeed we find that this indicator function gives us values which are close to 0 in this path, which is what we have seen actually, but this was the average. So now we see some instantaneous fields, and well, although there's some fluctuations, still the values are not very big as compared to what we've seen in fully turbulent flow. So we can quantify this even more by computing the RMS of this indicator function over the time series, and this is the value for the path, whereas these are the values for the fully turbulent flow. So previously we had found values which were even above 0.4 for these marginal Reynolds numbers, and then this value would decay, meaning that for higher Reynolds numbers we would get an 8-vortex state even instantaneously. The path has values not close to 0, but substantially lower than marginal Reynolds number turbulence. So what we can say is that actually the paths seem to be instantaneously more probable to be in a 4-vortex state or equilibrated vorticity over the cross-section than the marginal turbulence. So this brings me to the conclusions. First of all, we have established that paths do occur in square duct flow. We have found that they can be sustained, self-sustained, and then that they are in equilibrium in the sense that they don't spread in the range between 800 and 1025 for the bulk Reynolds number. That statistics in the core of the path are similar, let's put it carefully, to marginal turbulence. And we have not detected any clear instantaneous 4-vortex state in the path. So finally, one thing that's outstanding is how these paths connect to possible traveling waves, which, as I stated, however, are not available yet in the square duct. Thank you very much.
Some questions?
Yeah, just on the Reynolds number, what's the definition of the Reynolds number again? I missed that. Is it the
Bulk velocity and the half width.
half? Okay,
Yes.
because we did some experiments 3 weeks ago or
Mhm.
something. We just started. We found them halves at 1,500 or so. That matches.
Okay.
Okay.
In the case of pipe flow, one difference between a puff and a slug also shows up in the profile. That it's sort of the slopes at the front and the back are different in the two cases. Do you see something like that in square duct as well?
I mean, the front
So
and the
when
back are
it's-
definitely different. I mean, the puff is completely non-symmetric. So,
But when it's not, but the slugs that are growing in pipe flow have sort of
we haven't
symmetric
gone.
front
Yeah,
ends,
okay.
things.
So we haven't analyzed in detail the slightly higher Reynolds number above it. That will be the next step as well. You're right. But even the puff itself is completely asymmetric. I mean, if you look at the profiles here and here, they're not at all the same.
Okay. Heather? Yeah.
Could we see again the 8 vortex
Mhm.
state that you had? Because it looks more like a 16 vortex state to me. Forces separate again near the core. You get,
You mean here?
yes. I would think the Reynolds number in that region, the local Reynolds number, is really quite small.
Yes. That's possible. So
In which case, you might well end up with a whole hierarchy of little eddies.
okay. Well, the question is, what's the intensity of these small vortices here? I mean, also, I mean, this is a 65 by 65 grid. I don't know how many vortices I can resolve there. So,
Okay. Yes.
You mentioned that one way of doing this would be to reduce the Reynolds
Mhm.
starting from turbulence. Has any actual work been done?
yes, actually, we have done. Let me show you. I was talking about those, but actually, in the cloud of data I've shown you in the beginning, actually, the majority of them were for reducing the Reynolds number. So all these S cases were done reducing the Reynolds number from turbulent flow. All these M cases were done with the forcing.
There's some experimental data on channels that I and Srinivasan did one ago,
Yeah.
reducing Reynolds numbers and seeing where the critical Reynolds.
On pipes.
It was on.
Okay. We have time for one more question. Yes.
Could you describe a little bit more the transition between the, okay, on average you have the 8 vortices, but how do the 4 vortex system look, and is it a kind of characteristic time scale to go from one system to the other?
Well,
But I want to see them, could you just draw? I mean,
just draw them. I mean, they look exactly like. I mean, they look pretty much like the 8 vortices. You can just
Yes,
superpose
just
4 and 4. They look very much the same. Actually, the argument is that at the very low Reynolds numbers, since these vortices are created by the signatures of the coherent vortices of the near-wall turbulence, actually they're quite big in outer units. So the argument is that when the Reynolds number is very low, not at the same time the cross section is too small to accommodate 8 vortices. Okay, so only 4 fit instantaneously, and the system can switch in those in the two states.
because you were explaining something about the fact that it's like only 2 walls are active.
Yes, they always
but
appear
I want
in
to feel it
pairs.
physically
No, they
better.
always appear in pairs. So sorry. So if you have a okay. So you either have one pair here and another pair here,
That's what I
or the other way around.
That wasn't clear to me what you mean by your
Mhm. No,
and
it's like that.
alternate with the other. Okay.
But they are completely consistent in terms of their rotation later with the signature. So.
And is it a kind of characteristic time for going from one state to the other?
That's also a function of the bulk Reynolds number. Can't tell you exactly what the scaling is. Sorry.
Okay. I think we'll stop there.